Hello, my name is Kirthna Kumar, and this is my Lab 5 lab report, Magnetic Braking with Faraday. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of copper and comparing the results with a created computational model. The experiment setup uses a bar magnet, a copper tube, information from the previous lab in the form of the mu dipole, or the magnetic dipole, and coding for the computational model. The system in this instance is the bar magnet and copper tube, and everything else is considered the surroundings. So the overall results when dropping the bar magnet from a meter away without the tube, it was around 0.6 to 0.8 seconds. The experimental time when dropping the bar magnet through the tube was around 12 to 13 seconds, and the computational model provided that the time was 13.1 seconds for the magnet to drop through the copper tube. So the main physics ideas in this lab were Faraday's law, Biot-Savart law, and Newton's second law. Faraday's law describes that the negative change in flux over time is equal to voltage, and this is seen in the code. Biot-Savart law is shown here with its formula, and in this experiment it's used to predict the magnetic field of the magnet as it travels through the copper wire. It comes in this form in the code as well. And then Newton's second law describes the concept of F net is equal to mass times acceleration, which is used in this experiment to calculate gravitational force on the magnet. And in addition, it also accounts for the update velocity and position formulas. So this is the experimental data that was collected. These were the tube dimensions and the magnet properties. And then the times provided here for each trial when dropping with the bar magnet without a tube, and then when dropping the magnet through the tube, these are the times for each of the trials. Some assumptions for this experiment were that the bar magnet acts as a magnetic dipole because it has the north and south features on it, and the only forces acting on the magnet were gravitational and magnetic forces. So the coding portion of the lab, here we are setting up the physical constants, geometry of the tube, and properties of the magnet. So for the physical constants, the resistivity had to be changed from aluminum to copper. This is the dimensions of the tube. It should be noted that the length of the tube was 1 meter, around 1 meter. However, to account for time and to make the program run a little faster, we divided length by 10. And then for the mu dipole or magnetic dipole, with the information from the previous lab where dipole was equal to 2.15, the model did not accurately reflect the actual experimental time it took to drop the magnet, which was around 13 seconds. And so this was adjusted to 1.2 in order to reflect that. And the second part was creating the magnetic field of the object, where this code is based off of the previous experiment and as a function creates the magnetic field of the bar magnet. Part 3 is when we calculated the change in magnetic flux, which is based on the derivative of change in magnetic field and multiplying it by area. And then to calculate current, we divide velocity, which is equal to negative flux over time divided by resistance, and then calculating the B field at each ring and using that to calculate magnitude of magnetic force is seen here. And then step 7 calculates the net force by adding up the gravitational and magnetic forces, and 8 uses the net force previously mentioned to update the position and velocity of the magnet. So this is the visual model that the code creates. This side is a visual representation of the bar falling through the tube, and then this side is the chart that was created in which it shows that the bar magnet took 13.1 seconds to reach the ground or fall through the tube. So to interpret the simulation, the total time in the tube was much larger in the computational model than the real-world system. In order to make it more accurate, the magnetic dipole was adjusted and also accounted for possible human errors. And the shape of the plot previously seen tells us that gravity has more of an effect when entering or exiting a tube, but is relatively the same as the magnetic force within the tube, which is why velocity is seen as constant in the middle, but is drastically different or drastically lowered at the ends of the experiment. Possible sources of error include friction between magnet and tube, air resistance, inaccurate measurements, and adjusting for the magnetic dipole. Based on Ohm's law, if the resistivity reduced, then the current would increase to compensate and reach goal voltage. This current increasing would lead to overall magnetic field increasing and slowing down the magnet. And if there were holes or slots into the tube, then the overall magnetic field would be weaker and would cause the magnet to fall faster.